Alright guys, we're going to kind of pick up where we left off yesterday. Do a couple examples with the segment addition postulate. There's a couple vocabulary words in we're going to introduce. And then by that time, probably go to lunch. Alright, so this question, before we get into anything, when you guys go through my PowerPoints and we'll go through them in class, and we skip around or we go over like all of the 18 slides, we'll hit 9 of them. It's because the other slides are probably most likely either extra information that we can talk about if we have time, okay? But maybe it's not information that the state of Ohio says is the standard that we need to cover immediately, or they're extra examples, okay? And the amount of examples, we do not have enough time in this class period, in this school year, to go through enough examples in class, okay? We're going to see a handful at most, okay? And every problem is going to have its variations and stuff like that, and it's going to just be impossible for us to cover all potential variations. So I'll try to give you a good snapshot in regards to the ones that we do in class, okay? Give you a good collection of them, but I'm also going to leave extra ones in my PowerPoint. So if you need extra examples, you don't have to go digging through the internet or digging through textbooks or whatever to find extra examples. You can look through the PowerPoint and find the ones that maybe we haven't talked about yet. Okay? And then if you, in the event that you do that, you need some validation on your solutions, that you're doing things right, come see me, talk to me, and I can give you those solutions or work them out with you. Okay? This one, I haven't done a very good job of labeling things here. Let's just call this R. Let's call this point S. Let's call that point T. Right. So I'm going to give you a worksheet in a couple days. It's going to ask you to do some kind of preliminary work in regards to solving this. Because a lot of people are going to just want to jump in and start writing down the algebraic equation to solve this. And I want you to kind of slow down a little bit in regards to doing that. Because I think initially these types of problems, yes, that's probably okay for most of us. But eventually when the questions start to change and things start to get more difficult and we start removing algebraic expressions and just dealing with representations like RS and ST and RT and stuff like that of segments, that we understand the process that I'm going to show you in a moment, okay? And if we can do what I'm going to show you in a moment, it's going to make those harder problems later on a lot easier to kind of mess around with, okay? So I'm going to write this statement down. It's just going to say write an equation using segment addition postulate. Okay? And right here, I'm just going to write above equation, I'm going to write the word general. Okay? Just a general equation, meaning not a specific one, not one that uses 7x, 5x minus 3, and 45, but a general one that uses RS, ST, and RT. Is that going to make sense? So when we write that, and this is the way I want you guys to kind of think about this, just like you're reading a book. You read a book left to right, correct? So as I'm looking at this and I'm trying to figure out these components, I'm going to come across the first letter, which is R, and I'm going to get to the second letter, which in this case is going to be S. So RS is my first segment. Okay? I'm then going to, I said take my break there, I'm going to pick back up, and I'm going to travel from S to T, right? If I were to sum those two things together, I went from RS and then to ST, that would be equivalent from walking from R straight to what? T. And that's what I want us to be able to do. Hopefully that it doesn't take us that long when we're doing it on our own. But RS plus ST equals RT. Now I want you to write it that way left to right, because there's several things going on there. One, if I I look in the middle here, those letters are the same, right? So it tells me both those segments both share S. So it tells me that they're kind of consecutive segments. They're intersecting. Does that kind of make sense? And the fact that we know that they're collinear, if I look at the first and last letters, those first and last letters tell me what the total should look like. Should look like RT. That kind of makes sense to everybody? There's absolutely nothing wrong with doing it this way, but I want you to avoid it, where I say SR plus maybe, I'll be saying that there. SR plus TS is equal to TR, okay? Because when I look in the middle over here, that same letter is not showing up in the middle, okay? You're seeing the same letter on the outsides there, okay? And I think that's an issue sometimes, okay, the way we should view things. This letter is between R and T, so when we write it this way, I want that letter between R and T in our general equation. Does that make sense? And I think that'll just make your life a little bit easier down the road if we can follow that procedure. All right, so now that we have that, you've done all the geometry. Okay, so if you can do that, you are an exceptional geometry student so far. Okay, and my hopes are that you would agree that that wasn't very difficult. And throughout the year, you're going to find out that the geometry in itself is not very difficult. Okay, it's the work that these tests that we're going to take make the distinction, or allow them to make the distinction whether I'm a good geometry student or not. Because they're going to be, when you type an answer into Math Excel or the end of course exam platform or whatever, they're not looking for RS plus ST equals RT. They're looking for what X is equal to. Because if you can tell me what X is, then they can say, well, we can work our way backwards. If you got X right, you got everything before that right, so you got the geometry before that right. Does that kind of make sense? So the hard part, the place that people struggle with in this course is not the geometry. It's the algebra that kind of validates whether you've done your geometry right or not. Okay? So we're going to now substitute. So RS, what do they call it in our picture? What is another representation for RS? Anybody? Correct. 7x, that's fine. Okay? So we make that substitution. Replace RS with what it's equal to. So then what is ST?
5x minus 3.
Good, 5x minus 3. Okay? We've made those substitutions. Now we're going to make the substitution for RT. 45, right? Okay. So again, it's a little bit of algebra substituting, but now we've got to go through the algebra skills that we learned last year to validate whether I've done the geometry right. Okay, so we'll go through how many x's do we have up there?
2.
How many?
2.
How many? You visually see 2 written down, right? But that means you have 7 of these right here, and you got 5 of those ones. So collectively, you should have 12. Okay? So 12x minus 3 equals 45. We're going to do what next? Add 3. So 12x equals 48. And what's x going to be then? X is 4 divided both sides by 12. Okay? So now on Math Excel or the Ohio browser, when you take your end of course exam, when you type in 4, they're going to say, okay, that means that you were able to set this up correctly, which means you were able to set that up correctly, which that was the geometry. Because you got 4 right, you got the geometry right. Does that make sense? Okay. Where, if you didn't get 4, okay, you didn't do all of this stuff right, it doesn't necessarily mean you got that wrong, right? I get people all the time to get this right, but they struggle in their algebra. Their algebra is what provides them kind of their hiccups in their process of being evaluated as being a good or bad geometry student. Okay. The way I compare this is, you all can do calculus. Okay. You guys know what slope is, right? You guys know what area is, right? Okay. So if you know those things, which you probably learned, slope in the 7th, 8th grade, 9th grade, area probably even before then, Those are the two components of the calculus. That's all you're talking about in calculus, slope and area. Okay? But the algebra that allows us to address those things is extremely difficult. Okay? And people struggle with the calculus, not because of the calculus ideas, but because of the algebra that's used inside of it. Okay? Same thing in geometry. Okay? If you're bad at algebra, it's going to be hard for me to determine whether you're a good or bad geometry student. All right? Does that kind of make sense? So a lot of times throughout the year, you're going to hear me say, now you've learned the geometry, so now let's see if we can remember what our algebra tells us. Okay? Now if that's 4, if x is 4, and I haven't really specified in this question what I'm looking for, let's go ahead and find out what this distance r to s would be. What would rs's length be if x was 4? It would be 28. So just plug that back in and evaluate. What would this one be? 17. Okay? And there's a couple things we can do to check this. We could say, 28 plus that 17, add those together, it gives me this 45, which I'm able to replicate a value that I started with. So that tells me that my 4 is probably right. Okay? Another thing you could have done is, instead of plugging the 4 in right here and evaluating to get 17, once I had this to be 28, can I take 28 and 45 and subtract those and get 17? All right, then how can I check that? Well, I'll take my 4 and I plug it in right there, and that gives me 17 as well, right? Okay. So that's a nice way of being able, with these segment addition questions, to be able to check yourself. You should always be able to do that, and it's usually just an additional step of addition or subtraction. It's going to allow you to validate whether you've done things correctly. Okay. So give you kind of an example of what would look like if you did something wrong. Let's say I found x to be, let's see, it would be a common error here. I don't know what a common error in that question would be, but let's just say you found x to be 5, just to quicken things here. If x was 5, okay, I come up here, plug things in, you'd get 35 there, right? If that's 35, what's this yellow segment ST supposed to be? It's supposed to be 10, right? If I go off the idea that the whole thing's 45, so 45 minus 35 should give me 10. But if I plug 5 in, what do you get if you plug 5 in? 22, right? Are those numbers the same? Well, there's a discrepancy there, right? So that tells me that 5 wasn't right. Okay? When you check yourself, you should be able to replicate that second value. Okay? I think we said, what was it, 17. You should be able to replicate that 17 2 times different, and get the same result. And if you can't do that, then you've done something wrong. Now, my suggestion to you, if you check yourself and you find out that you're wrong, the number one thing that people do is they just crinkle up their page and throw it away, or they take their ink pen and they scratch over it, or their eraser and they erase everything. A lot of times it's a real simple mistake. Like here, what I get a lot of people to do, instead of adding 3 to both sides, they subtract 3 from both sides, or it's a sign that they've messed up somewhere. So don't erase things. Start back and just trace through. Go through what you did again, cautiously, pay attention to detail. Make sure you've done everything correctly, because it could be a 10-second fix. Does that make sense? All right. But if I scrap it and start over from scratch, now it might be a 3 or 4 minute fix, and that's a problem. Okay. Especially if you're on a time test like the ACT. Okay. So when you're wrong and you know you're wrong, don't just throw everything away. See if you've made just a slight algebra mistake somewhere. All right, I'm going to give you a little bit of time to do one of these examples. Let's do that one. I want you to write the general equation with just the letters, okay? And then start substituting and go ahead and solve. And I don't have directions. Let's just solve for m. Solve for m, and then when we get that together, we can find out what those distances are. Alright, so one of the things that I'm really bad at is kind of judging the time it takes collectively all of you to kind of work through a problem in an exam. So sometimes, I might give you too much time. Sometimes it seems like I just gave you the question and I start talking right away. So I apologize for those types of things. But do you guys agree with what I have written up there in red, that QV plus VU equals QU? Okay, so that's working left to right, starting Q, walking to V, and then starting V, going to U. If I add those two distances together, it should be the same as walking from Q straight through to U. Okay? So now I just start substituting. So try to color code things here a little bit. That first QV up there in the picture, it looks like they're showing 4m minus 7 to be that distance. VU is what I've got written here in green, 3m plus 6. Okay? And I said that's that distance. And it is that distance, but it's just an algebraic way of representing that distance. Does that kind of make sense? Once I know what m is, let's say, I don't know what m ends up being here, but let's say it was 10, then I know what those two distances are numerically, right? Okay? And then obviously QU, the entire thing we're looking there at as 85. Is that all right, everybody? Okay. On this one, I didn't do a great job of putting the curly braces and identifying things like that. Sometimes you're going to see questions like this where they're not as explicit in regards to their detail as maybe what we are in class or what you've seen in the previous examples or something like that. A lot of times throughout geometry, they take their expressions and they just jam them close to the object that they're supposed to be attached to. Okay? So try to do that here. So when we work through this, how many m's do we have up there? 7 m's, right? So we're going to add those together. I'm going to add my constants together. So that gives me -1. And that should give me 85 as a total, right? Okay. I'm going to add 1 to both sides. So it gives me 7m is equal to 86. Okay, so if I look at that, now I'm thinking, how many times does 7 go into 86? And I know 7 goes into 8 one time, right? And that would leave me with 16 left over. Does 7 divide 16 evenly? No, so that's not going to work out real nice. So what I want you guys to start getting used to in this class is m is just, we're just going to leave it as 86 over 7. Okay? Now, I know some of you are wanting or we have the desire to know what that is as a decimal. If you want to do that, go ahead and do that. Let's see here if I open. I like Desmos. I like using this calculator. Let's see if I can clear all this. So 86 over 7 gives me that number right there, which that is the value then for m. Okay, now let's just kind of work through this real quick and see if that does provide me with 85 as a total. Okay, so I'm gonna just plug in my solution of 86/7 to that m right there and that m right there. So what's going to happen is it's going to look like this: 4 times 86 over 7. I'm going to add to that, subtract to that 7, and then add 3. 86 over 7. I'm going to add to that then 6. Hit enter, and you see that it does then spit back. That is indeed 85, right? Okay. Now, if I'm a person, if I need to know what QU is, okay, I've got options. I could plug that back, and I'm not going to do it right now just for the sake of time with you. But you can plug that 86/7 back in and multiply it by 4. Okay, and that's going to give you a pretty large numerator here over 7, whatever 86 times 7 is. Sorry, 86 times 4 is. And then you could subtract 7 from that by using our rules of fractions, by common denominator, and then subtracting the numerators. Okay, I'm not going to work with that with you right now. I do know that we probably struggle collectively. I'm not saying individually that you are bad at fractions, but as a group, we probably need some practice with fractions. Okay, because what have we done in the past? We tried to do what with fractions? Avoid them, right? Yeah, we try to get away from them. You might have had teachers in the past saying, well, your fractions, use your calculator, use the ABC button on your calculator. You guys ever hear that before? Okay, well, doing that does not get me better at using my fraction rule to be able to address those things the way we need to. Because, like I said, it's about knowing why and not just being provided something. With your calculators, you could type something in, thinking you've typed it incorrectly, but it spit back the wrong answer. And you had absolutely no idea that was the wrong answer. You just took their word for granted. We need to know why. So we need to work on those rules and those properties, and we'll do that provided the time here eventually. Okay. Is that enough examples with this segment addition? You guys kind of feel comfortable with it? Now I know there was a hard one at the end of the assignment that's due tomorrow. If we have time, we will come back to that before you guys go to lunch. I want to talk about a couple other vocabulary words and concepts that allow you to work through all of that assignment correctly. And the first one here is going to show up on slide 8, and it's just identifying the concept that we have about congruency. Okay, when two shapes are congruent. So when two shapes have the same size and have the same shape, okay, that is enough to classify them as being congruent to one another. Okay. Now, when we say size, same size, I don't really care what the size is. I don't even really need to know what the size is. Okay. The idea of congruency, the way I want you guys to think about it, to envision it or visualize it, is it's kind of a cut and paste idea. If I could take shape number 1, cut it out, move it around, rotate it, flip it, whatever I might have to need to do, and then lay it directly on top of shape number 2, and it's a 100% match. Okay, there's no overlay or anything like that, then the shapes are congruent. Is that all right? Okay, so it's a direct cut and paste overlap. If they overlap 100%, we say they're congruent. And once we say they're congruent, it tells us, well, they had to have been the same shape, and it tells us they also had to have the same size, and whatever that size may be. And there might be multiple things that are dictating that size. The key thing for having the same shape, obviously, a segment has to be congruent to a segment. A segment cannot be congruent to a square. A square cannot be congruent to a triangle. Okay? They have to be the same shape. So that's pretty obvious. The size thing is what we'll focus on a lot in this class. Okay? Is that okay? That's what congruency means. Equality is different than congruency. Equality is simply the argument or the statement that two numbers are the same. Okay? Or two measurements are equal. Okay? So that's something to think about. Equality and congruency are different. Okay? Equality is when we're talking about numerical expressions being the same amount. Okay? Congruent segments, obviously, this is just essentially saying that they're the same shape and the same size. The shape says, the shape part here is that they're both segments, and the size part, the only thing that dictates the size of a segment is its length. So those two lengths are the same for both segments. So in this case, I've got these two segments. If I tell you that they're both segments, if I tell you that that's 8 centimeters and that's 8 centimeters, you can make the argument that they're congruent and that you could cut and paste the red one and lay it directly on top of the purple one, and it's going to be a 100% match. Okay? Or vice versa, the purple one on top of the red one. Okay? And if I tell you one of those is 8.1 centimeters and the other one's 8 centimeters, okay? Are they a complete match? So they're not congruent, or what we say, they're incongruent, okay? Now your eyes, think about this. If you're sitting where your seats are, and I told you that one of those is 8.1 centimeters and the other one's 8 centimeters, would your eyes be able to tell that difference? Probably not, okay? So you never want to go off of looks, is what I'm trying to get at here. You always want to go off of what they're telling you, whether they put numerical quantities in there or they might use some type of notation. Okay, and hopefully maybe you've seen this before. If those two are congruent, a notation that we'll use is we'll put hash marks inside those lines or those segments. And whenever I see those hash marks, anything that has one hash mark is now congruent, or we're saying it's congruent to anything else that has one hash mark. Have you seen that before? Okay. Now, let's say I bring into this picture some other things. Bring these over. All right, don't worry about the colors or anything like that. If I do that, if I want to say those two up top are congruent to one another, if I want to say these two are different, okay, then I have to make sure that there is a differentiation in regards to how many markings are in those two that are different. Does that kind of make sense? Since that one on the bottom has nothing in it, then it's showing that it's different than that one, right? So if that one's 8 centimeters, that one doesn't have a mark in it, so that one cannot be 8 centimeters, right? If I do this, I've now shown that the bottom two are congruent, right? The top two are congruent, but are the red ones congruent to one another? No, because they have 1 and 2, right? Are the purple ones congruent? No, okay? So, and a lot of times, if I've got maybe another set of segments that I want to show congruent, okay? I go to 3 kind of tick marks or hash marks inside my line. I go to 4, I go to 5, however many I need. Okay, so that's the kind of the symbolism in our pictures that we will go through to determine whether something's congruent or not. But you never, ever, ever, ever want to look at a picture and visually say, those are congruent because they look like it. Okay, you never want to do that. Okay, it's like coming up to a stranger that you've never met before and say, "I look like a good guy." You never want to do that, right? You don't know that person. They could be a total bad person, for lack of a better word. But they might dress nice. They might be kind of formal to your face and that kind of stuff. But they're inside are a very, very bad person, right? So when you do those types of things, you get yourself in trouble, okay? So if I'm in geometry class and I go off of looks, I'm going to get myself in trouble, all right? So just be careful that we have to be told a lot of stuff before we can make arguments. Okay. So that's the idea of congruency, and that turns out to be one of the kind of the driving forces in this course, is that we're going to deal with trying to prove and show why some shapes are congruent to other shapes, maybe at some point show why they're not congruent, maybe start talking about inequalities and that kind of stuff. So understanding what congruency is and understanding what equality is very important. Okay. So when we look at these two things, it says to show that segment AM and segment TZ have equal lengths. Okay. Now if they have equal lengths, we're talking this, that the measurement of AM, or the length of AM, is equal to the length of TZ. That's how we would write that to show that their characteristic, their size, that explains something about that shape are equal. They're numerical values that are equal. We do it that way. We use equality. Okay? So that's essentially telling us that even though I don't know what the numbers are, the numbers that represent those two shapes are the same number. Does that make sense? Okay? When I want to show that two shapes are congruent, we use that notation. I have to talk about the shape, so I use the segment symbol above them. I say segment AM and segment TZ, and I use that congruency symbol in the middle. That equal sign with that tilde over the top of it. That's the read that segment AM is congruent to segment TZ. And what that tells me is that the shapes should be able to be cut and pasted and laid on top of one another and match 100%. Okay? What's important is that this here kind of encapsulates two things. It tells me the shapes are the same and the size is the same. So that tells me that the distances or the numerical characteristics are equal. Okay? When I say AM equals TZ up there at the top, that doesn't necessarily tell me congruency all the time. Does that make sense? Especially with other shapes. All right, so just have to be careful with that. And if that doesn't sink in right now, kind of confusing maybe right now, we will talk about that a lot for the rest of the year. Okay? So at some point, in the next couple of weeks, congruency and equality and the difference between them is going to be very clear to you. These are two vocabulary words we need to talk about. First one pretty easy. Okay, breaking that word apart again, the prefix mid meaning middle, point actually meaning point. So middle point. Okay? So the midpoint is the point that divides this segment into two congruent segments. Okay? The point on a segment that divides the segment into two congruent segments. All right, so a conclusion that we get from this, and I should probably write it this way using the terms that they're using, congruency. All right, if M is the midpoint of segment AB, then what this tells us is that the segment AM, from one endpoint up to my midpoint, is congruent from my midpoint to my other endpoint. Okay, so graphically, hopefully that's not too confusing to visualize. Let's see if I can add a picture down here for you. So that's A, that's B, there's my midpoint, okay? What that's saying obviously then is from A to M, that distance, that segment is congruent from M to B, okay? Meaning I could cut this segment off and later on top of that one, they match up perfectly. What is really beneficial from this, guys, is what this allows us to do with some algebra. Because if segment AM is congruent to segment MB, then the length of AM is equal to the length of MB, and that's going to allow us to do a little bit of work with some of these problems maybe you've seen in your homework that you haven't addressed yet. Okay? Again, we have to have these markings down here. Okay? If I look at these lines without these segments without the markings in them, even though I think I've done a pretty good job of locating where M might be or the midpoint might be in that segment, if I were to actually take a very, very precise instrument and try to measure those distances, AM and MB, I'm going to probably find out that they're different. Okay? I'm probably going to find out that M is probably maybe a little bit closer to A. Your eyes can't really tell that, right? Okay? You have to be told. Until you make the conclusion that M is a midpoint, whether it tells you in words or in symbols like that or notation like that, now you know it's a midpoint, and now you know those two distances are indeed the same.
So they give you the midpoint, like you don't create one?
Right, most of the time. Okay, there might be times where we can do a little bit of work to develop the location of one, but most of the time they're going to tell you this point's a midpoint of this segment, or this line passes through the midpoint, or something like that. So we'll have some tools somehow to find the midpoint, and it'll be provided for us. Good question. So then that gets us to the next question, or the next vocabulary word, which is I don't like the way this is written. So I'm going to delete this. We'll call it segment bisector. Segment bisector. The word bisects, or bisector, bi meaning to, sector meaning parts, right? Does that make sense? So you're going to break something up into two parts. And because it's a segment, that's what's getting broken up. A segment getting broken up into two parts. Okay? That's kind of breaking it down using our English, but there's still a geometry concept to it, and that geometry concept is that those two parts that get created are congruent to one another. Okay? So a segment bisector, by definition, is a line, a segment, a ray, or a plane, any one of those four things, that intersects a segment at its midpoint. If it intersects it at its midpoint, it creates two congruent segments, right? Okay. So I give you kind of a visual of these four things that are providing us a segment bisector. So let's see here. All right, so I have right here that red line. That's just my segment, okay? Get rid of these other points. I might have one of those. Never mind, let's keep those. All right, so if I look at that segment, you guys can see that from A to C, it's saying it's 180.66. From C to B, it's 180.66. So that point right there is indeed a midpoint. Is that okay? All right. So if that point is a midpoint, a segment bisector would be any type of shape that I mentioned, line, segment, ray, or plane, that goes through C. So would you guys agree that that line right there goes through C? So that black line is referred to as a segment bisector of AB, okay, of segment AB. And really, guys, any line that passes through there, all of these lines would be segment bisectors. Is that okay? And if that line, or any one of those lines, is a segment bisector, then any portion of that line that is going through the red segment is an angle bisector. Sorry, is a segment bisector. Okay? So, what I mean by that, let's say I cut everything off from D and to the right, so let's get rid of that stuff. That's a ray now, right? Is it still going through C, the midpoint? So that ray is a segment bisector. Now that ray, you know, the part that's on either side of that segment, the top or the bottom, it doesn't matter how long it is, okay? It could be all the way out here, it could be real close to it. And that point D could actually be the midpoint. Does that make sense? Okay, so your ray could actually start at the midpoint of the segment. That's perfectly fine. That can happen. That being said, we can do this. We can say rid of the ray. Where'd the ray go? All right, so that black segment passes through the midpoint of the red one, right? So that black segment is a segment bisector. Now the red one is not a segment bisector. The red one, you see, is not passing through the midpoint of the black one, right? Okay, or visually, we could probably argue that it's not. And again, you know, that side can be as long as it wants. This side can be as long as it wants. Okay? And the segment can actually start at the midpoint, so that would still be a segment bisector. Anything essentially that passes through the midpoint of the segment is referred to as a bisector. The plane one a little harder to see. Hopefully I didn't delete it too much to where we can't see this. Good. So this line FG or GF is our, the segment GF is our segment. H is the midpoint of it. Can you see that that plane is passing through that midpoint? Okay, Okay, so that plane is indeed a segment bisector as well. Whenever that deals with a plane being some object for us, or doing something to some other object, it's usually a lot harder to see because of the three-dimensional aspects, right? All right, so why do we need to talk about that? You've seen maybe in your homework a question like this, okay? And it says, it does say W is the midpoint of XY, find the length of WY, or segment WY. What happens, guys, is a lot of people look at this and they don't read this because they've gotten to have it. Well, the first question was segment addition. I go through it, get the answer. Second one, segment addition, go through it, get the answer. Third one, same thing, go through it, get the answer. And I become robotic, and I stop reading directions, and this one shows up, and I write down a plus 11 plus 2a minus 5 equals, and then I don't know what to put that it equals because it doesn't show me what xy's length is, right? Does that make sense? Okay? And they get stuck, and they start, well, I'm stuck, so I'm just going to do something silly. Or they start just throwing stuff up there and really not have any logic behind what they're doing. You have to read the directions. There's a lot of information providing the directions. It says W is the midpoint. So if W is the midpoint, we know that. We know that XW, that segment is congruent to WY. Okay? And if we know that, then length XW is the same as length WY, or that they're equal. And I have an algebraic expression for XW. XW's algebraic expression is a plus 11, right? WY's algebraic expression is 2a minus 5. And we should all be able to solve that. Move my 1a to the right-hand side, excuse me, 1a over here. Minus 5 equals 11. Add 5 gives me 16 equals a, right? So 16 is a. But I should be able to check myself to make sure that makes sense. Because when I plug back in, I should get two values, two distances that are what to one another? They should be equal. So I plug 16 in for that a. 16 plus 11, 27, right? 2 times 16 is 32, minus 5, 27. Any other number other than 16 is going to give me two numbers up there that are different. Okay? If I try 10, for example, it's going to give me 21 and 15. Not equal. So W could not have been the midpoint. Does that make sense? Like I said, the number one error is that people want to start doing this. Okay, so this is incorrect. Don't do it this way. They just get in the habit. Well, segment addition says a plus 11, and when I add to that the other part, 2a minus 5, set that equal to. Now I need the total over here. I need x to y, and they're not sure what that is because nowhere does it say that. So they say, oh well, I know it's 3 a's, right? Because that's 1a plus 2a is 3 a's, and that's a positive 11, that's a negative 5, so that's 6. So I got 3 a's plus 6. And my question to you is, doesn't that already, or isn't that already stated on the left-hand side of that equation? Isn't this another way of saying this? So what happens when I start combining like terms over here, I get 3a plus 6 equals 3a plus 6. And you see now that both left-hand side and right-hand side are identical, and we call this an identity. But what happens with every identity is that I start working through this. Maybe I subtract my 3a's from both sides, and I subtract my 6's from both sides. I get down to that, 0 equals 0, which is a true statement, right? Which is telling me that what I set up is 100% accurate. That is a true argument. But it doesn't lead me anything useful, okay? It didn't lead me to a precise, specific A like this one did. Is that all right? So as you're ever going through homework or a test question or whatever, and you do something like this, and you come down to saying, okay, my variables disappeared, I'm left with two numbers that are equal to each other, 6 equals 6 or 0 equals 0, go back to this and think, okay, that means that I have incorrectly used maybe segment addition postulate or something like that, and essentially I said the left-hand side of my equation is the exact same thing as my right-hand side, and that's a problem, okay? Everyone on the same page with that? All right, you should be able to finish that homework assignment. The last question on there is challenging. I'm going to suggest that you try to work through a couple of it, or a couple similar exercises of it before you go looking for help. But there should be a video on my website under section 1.3. It'd be last year's class, kind of working through it, that you can kind of open up and look at to get an explanation for them. We can talk about it again tomorrow as well. But my suggestion to you is try to fight through it first on your own before you go get help on it. Does that make sense? Okay. Have a great rest of the day.